Welcome back, class, to our next unit, and we're going to start this next unit with scientific notation, and that's most of the unit is actually scientific notation. We do a little bit with exponents, but today we are just going to do some of the basics with scientific notation, and your learning target is I can convert between standard and scientific notation. So at the very least, you should be able to do that after these notes. You probably remember some of this from the past. I think you might have done this before, and you might have seen it in science class too. You probably didn't do much with it, but you might have seen it. So scientific notation, here's what is it? It is a way to express very large and very small numbers. So if you're working with distances in space or lengths of viruses, those numbers are really big or really small, but either way they look really long on paper, or they potentially can. So scientists, people came up with a way of making them look smaller on paper when you write them out. And that's why it's called notation, as in the way we write it. And the product of two numbers, as it says right here, is, so it's a number between 1 and 10. So it starts off, and then we call it the coefficient. Down here, the coefficient. A number between 1 and 10. Notice 5.5 is between 1 and 10. 2.89 is between 1 and 10. It can be 1, so it can be 1 times something, but it can't actually be 10 times something. It can be 9.999 times something, but it can be 1 and it can't be 10. It has to be a single digit, and then the decimal, and then as many decimals as you want after that. And then we multiply by a power of 10. And as you probably have seen quite a bit in your life, when you multiply or divide by 10, a lot of times you just say, oh, add a 0. If you multiply by 10, add a 0. That's true, but what's really happening is the decimal point is moving to the right. So if you multiply 5 times 10, we think of add a 0, but really it's the decimal that moves over, allowing another 0 to be added. So if you had 5.2 times 10, you wouldn't add a 0. It's not 5.20, which is the exact same thing. It's 5.2. And then when it's 10 to the 5th, that means 5 tens, which means you move 5 times. So it's a really convenient way of just saying, hey, this is where the decimal really is, and we're showing it to you in this very short way. So in this example here, 5.5 times 10 to the 3rd, it really is the decimal moving to the right 3 times, and you can rewrite it as 5,500. And then when it's a negative 4, that's like dividing by 4 tens. Even though it says multiplying, it's the inverse. So it moves the decimal in the opposite direction. So this would be 1, 2, 3, 4, and now the decimal's right here. So this would be rewritten as 0.000289. I just confirmed that I moved it correctly. 1, 2, 3, 4. Yep. And that would be a very small number. So let's get some examples so you can try them on your own as we go. So it says write the following numbers using scientific notation. So we are starting with standard form. This is the standard form. And standard, it's called standard for a reason because it's the form that you normally see numbers in. And when numbers aren't large, we of course use standard form. But as numbers get bigger and bigger, this is 6 billion, we start to get a little tired of writing all these zeros. In this case, there are 9 zeros. We say 6. And in fact, we move the decimal 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. We want to move it from where it is, right here, to where we want it, which is so that there's only one digit before the decimal. So we say 6 times 10 to the 9th. And this number is how many times the decimal moved. So we'll say decimal moves. All right, let's try number 2. This is a small number. I want the decimal to be right there, and I want it to be there so that there's only one digit before the decimal and the rest are after the decimal. So I'm counting 1, 2, 3, 4, 5. So I'm going to say 1.5, that's where the decimal is now, times 10. Now you don't want to say 5 to the 5th power because that would make a very big number. I want a very small number, so I put a negative in. 93 million. Again, that's a convenient way to write it, but we can also write it in scientific notation as well. So I'm going to rewrite this. 93 million. Million has 6 zeros. This is where the decimal is if we don't do anything. And this is where I want it in scientific notation, so that I have one digit and then the rest. So 1, 2, 3, 4, 5, 6, 7. 9.3 times 10 to the 7th. Now we'd have to include all the numbers in here that are not 0. As long as we hit, now let me rephrase that. We write it until there's only zeros left. So if this said 93,050,000, we would have to still do the same thing. We'd move it back to the same spot so that we only have one digit, but we would have to write 9.305 times 10 to the 7th. So right there, there's only zeros left, so we don't have to write those. But we do have to include that 0 because there's still another number after it that is significant. All right, let's try the next slide. Write the following numbers in standard form. So now we're going the other way. I'm just going to do a quick, this is what I do when I look at a scientific notation number. This is the most significant part of this whole number here. It tells me generally how big that number is. That tells me I have to move the decimal 8 times to the right. I know it's going to be a very big number and not a very small number like this one here. So then I write all my numbers without the decimal. So all these numbers without the decimal. And the 8 tells me to move that decimal 8 times to the right. So I'm going to say 1, 2, 3, 4, 5, 6, 7, 8. And you want to be nice and clean with your swoops so that you have enough room to put the zeros in. You don't miscount. And if you want to put your commas in, you count 3 back, and there you go. 480 million. All right, the negative one, again, you write. Now I know I'm going to go to the left, so I don't start my number right here. Because if I do that, then I'm going to run out of room on my line. So I'm going to start it closer to the end. I'm going to hold my marker where the decimal was, and I'm going to count back 1, 2, 3, 4, 5. And that's where I want my decimal now. And I add zeros where there was nothing. All right, the same thing with this last one, 10 to the negative 7. That means I'm going to move back 7 spots, so I'm going to make sure I put this over here. Again, no decimal, but I put my pencil where the decimal was, and I move back 7. 1. Now sometimes I do this little trick. So I know it's 1. Now I need to move back 6 more times. So in this one I need to just add 6 zeros. And you can avoid having all the swoops that way. So 1, 2, 3, 4, 5, 6. I would just encourage you to count once again when you're done just to make sure you did it correctly. All right, a lot of times you're going to be presented with a number and it might not be in scientific notation, or it's a multiple choice question, and it might try to trick you into thinking that was the right answer, but it's not actually written in scientific notation. So the quest here is to figure out if it's written properly or not. And if it's not, we're going to fix it. So number 7, we got 1 digit, and it's between 1 and 10. If it's 1 digit, it kind of has to be. And the rest looks good. So this one, I give it my approval. All right, here we go. Here's the 1 digit, and it's 0. That's not between 1 and 10. So we have an issue here. We're going to have to move the decimal to the right and rewrite it as just 1. You can even write 1.0 if you want, but 1 times 10 to the... Now, we move the decimal. So we need to change the instructions on the 10. So that negative 5 can't be negative 5 anymore. So there's this little trick where you can use your hand. So if you hold up your hand so that it looks like this. So you're kind of making an L. although it doesn't really look like an L to you. I guess if you were looking at your own hand, it would look more like this. So if you're hold up your hand so it looks like an L to you, see this L right here? That means if the decimal moves left, the exponent goes up. So notice we move the decimal to the right, so the opposite is true. If we move the decimal to the right, the exponent goes down. And there you can even turn your hand down to make a little R. It's kind of hard, a little bit more difficult to... There we go. My hand skills are getting weaker. So if you notice, this is like a little R. So if you move the decimal to the right, the exponent goes down. Since we moved to the right, we want the exponent to go down, and it's already at -5. So when you go down 2 more, because we moved this twice to the right, it goes down to -7. All right, number 9. 10 is not between 1 and 10. Remember we said 10 couldn't be it because it's 2 digits. So we need to move the decimal from here 1 to the left. So that's 1 times 10 to the, now since we went left, we're using this rule, the exponent goes up. So 3 becomes 4. All right, number 10, 65 is way too big. So we need to move that to the left one, so it's 6.55. But again, we went to the left, so the decimal the exponent has to go up 1 notch. So from -2 going up is actually -1. You gotta be careful with that. Number 11, that one checks out. There's 1 digit, everything else looks good. And then number 12, there's nothing before the decimal, so it's too far to the left, so we gotta move it to the right once. 7.8 times 10 to the, and we moved it to the right, which means the exponent goes up. And there you have it. That is where we're going to end this video. I'm not going to leave you with anything, but we're going to have some practice problems when you come in, sort of prove that you understood what was happening. So if you got a little confused, you can go back through, cover up my work, and try it again, see if you can understand it. And we'll see you when you come in.